So in this talk, I would like to talk about the unitary subgroup of group algebras. But first of all, I would like to say some words, and I would like to show some notation corresponding to this talk. G for a group algebra. So FG denotes a group algebra over the group G with the field F. So in this case, F will be a field. And the following subgroup, which augmentation is equal to 1, it contains all the elements with augmentation equals 1, is called the normal subgroup of the group algebra. And it's a relatively large subgroup inside the unit group if the characteristic of the field is P and G is a P group. And it's well known the unit subgroup can be expressed as a direct product of the normalized group of unit and the unit group of the field. And I want to use the circle notation for an involution. An involution is an anti-automorphism, and we can define the unitary subgroup corresponding to any involution inside the normalized group of unit. It contains all the normalized group of units which image under this involution equals the inverse of this element. This notation was introduced by Novikov, and the linear extension of the involution of G, which sends each group element to its inverse, is called the classical involution. So it's a special kind of involution. It will be denoted by circle. So this will be the circle involution. And the main problem here to describe the structure of the unitary subgroups corresponding to different involutions. I define this set. G2 contains all the elements from the group G, which order equals 2. So G squared equals 1. And the maximum number of non-isomorphic unitary subgroups of the normalized group of units with respect to the involutions which arise from the group basis G was given in this paper. And if G is a finite group and lambda 2 denotes the integer for which the automorphism group for which the elements of order 2 in the automorphism group is a union of these conjugacy classes. So we have lambda 2 conjugacy classes inside the orders of elements 2 in this automorphism group. We prove the following theorem. Let G be a finite group and F a field. The number of non-isomorphic unitary subgroups of the normalized group of units with respect to the involutions which arises from G is at most lambda 2. So this is the maximum value. And we give a group which in this case this maximum number is reached. So if we consider the quaternion group over any field of characteristic 2, but this field should be finite, the number of non-isomorphic unitary subgroups in this group algebra equals 3, which is exactly equals lambda 2. And we have another example. This is the diagonal group of order 8 over the finite field of characteristic 2. In this case, the number of non-isomorphic unitary subgroups with respect to the involutions which arises from the group basis is 3, which is less than lambda 2, because in this case lambda 2 equals 4. So in this case the question, the main question corresponding to this isomorphism question, to determine all the groups for which this upper bound is sharp. I will use C2 to the power n for the cyclic group of order 2 to the power n, and I will suppose that n is greater than 2. It's well known, the automorphism group of the cyclic group, isomorphic to this direct product. And it's easy to see that this will be the value of lambda 2, so this will be for this special case. And let's consider the group algebra FC2 to the power n. So we consider the group algebra of the cyclic group over a finite field of characteristic 2. In this paper, we proved all the unitary subgroup, which corresponds to an involution which arises from the cyclic group are not isomorphic. So in this case, the number of different involutions equals 4. So this upper bound is sharp. And another problem corresponding to the unitary subgroups is to determine the order of the unitary subgroups corresponding to the classical involution. So in this case, I suppose that the involution is the classical involution. Bodhi and Rosa proved this result. So it's true for locally finite P groups. The order of the group, the unitary subgroups, depends on the order of the group basis and the cardinality of the field. So in this case, the field is also a finite field. And I forgot to write, in this case, P should be an odd prime. So it's not true for 2. So if the characteristic of 2, this equation is not true. Unfortunately, for the 2 characteristic case, this question seems to be a challenging problem and only partial solutions are known. In the group algebras, it's not an unusual situation. Typically, the 2 characteristic case seems to be the most hard cases. So we have a conjunction in this area. So let G be a 2 group and the F is a finite field of characteristic 2. Then the order of the unitary subgroup is always divisible by this expression. It depends on the order of the group and the number of elements of order 2 and the cardinality of the field. Actually, this sentence seems to be true for some n. We have some results in this area. Bodhi and Sakaj proved that n equals G2 if G is a finite abelian 2 group and finite field. And Bodhi and Rosa proved this, give some examples for this conjecture. If we consider the diagonal group, for the diagonal group n equals 4, and for the n equals 1, and for the generalized quaternion group n equals 4. If G is a non-abelian group of order 2 to the power 4, this n can be computed using computer. We found n equals 1 for these 3 groups, n equals 2 for this next 3 groups, and n equals 4 for the quaternion group for this semi-direct product and for this direct product. And if omega denotes all the elements from G, which can be a square of an element, so it contains G squared when G ranges over G, and theta denotes a set of groups which satisfy the following: g to the power h equals g. This power means the conjugation. So the conjugation of g by h equals g, or g conjugation by h equals inverse of g. We give a recursive formula how to compute the order of the unitary subgroups. If C is an element from the center of the group, and it should be an element of order 2, but not belongs to this omega, and the factor group where C is the generated subgroup by C. So if we consider this factor group, and this factor group corresponds to theta, the order of the unitary subgroup can be computed by using this recursive formula. So thank you for your attention.